Okay, I cut that last video off because I started to go off on a bunch of tangents. And my body was telling me by the fact that I had to go in the back room and cough. Okay. Allergies raining right now. With about a 99.9% certainty. Okay. Okay, so we got this. Well, what else can we analyze? We can analyze the acceleration. Okay. Now that gets a little more complicated because, of course, you've got to use a chain rule here. So you're going to end up with 3 terms on the I and 3 terms on the J, but then K is just going to be constant. Okay, so that's going to be careful with the signs this time. Negative sine t minus sine t minus t cosine t times I plus negative cosine t plus cosine t minus t sine t j. Now something is wanting to bother me about this, because there should be a kind of a dual nature to these, and the sines don't add up to 0 here. The cosines do add up to 0 here. And that kind of that disturbs my intuition a little bit, so I want to double check that. Okay, so I just want to go back to here. Derivative of t cosine t, you're going to get a cosine t, and they're going to get a negative t sine t. That's all right. And then with the t sine t, you aren't going to get a negative on the sine t. You won't get a negative on anything because you're taking derivatives of the sine. So it looked like I had a negative sign there. That shouldn't have been there, so this shouldn't be negative. And now you have a duality here. You got a couple of signs that are negative. You got a couple of cosines here that are positive. And then you have a negative t sine t and a negative t cosine t, and that's going to work out pretty nicely, okay? So, first thing you can say about the acceleration is that its magnitude is what? Well, this is going to be a 2 sine t, this is going to be a 2 cosine t, okay? So when you do a 2 sine t and a t cosine t quantity, 2 sine t, I'm just going to do 2 sine t plus a t cosine t. Ignore the negative signs because when you square it, everything's going to end up positive. And you can work that out and see how that's going to work because you might not see that far ahead. And I, in seeing that far ahead, could be wrong. It seems pretty obvious to me. It'd be the negative of the quantity you get when you do the 2 sine t plus t cosine t, and the negative goes away when you square things. Another way of looking at it. So anyhow, you're going to end up with 4 sine squared t plus 4 t sine t cosine t, and then got to write it cramped up there a little bit, plus t squared cosine t, that quantity plus kind of the dual quantity here, which will be 4 cosine squared t minus 4t sine t cosine t plus t squared sine squared t plus 1. And then these two add up to 0. And you're going to end up with a 4 sine squared t plus 4 cosine squared t. That's just going to give you 4. And again, I'm going to say magnitude of a squared. Instead of trying to put that square root sign over all this stuff, I'll just do magnitude of a squared and then put a square root at the end in the next step. Okay. Anyhow, you're going to have a 4 from this. Okay, then from the t squared cosine t plus t squared sine squared t, factor out the t squared. You've got t squared times cosine squared plus sine squared, which is just t squared times 1. So you have plus t squared equals 5 plus t squared. So that the magnitude of A is the square root of 5 plus t squared, if I did that right. Now the catch is, if you're riding this, this is an amusement park ride, and of course if it's an amusement park ride, you better stop somewhere. And you better have a phase where you slow down. You don't want to get up to the top at its maximum speed, and then just let you go. You become a projectile. And that would be interesting in itself. Yeah. Projectile motion. You have 3 dimensions, but your acceleration in the z direction is constant. The acceleration in your x and y direction, if you ignore air resistance, which you'd better do, because it's really complicated if you don't. And you do differential equations, of course, before you can even think about it. But then you have 0 acceleration in the x-y plane, so you're just going to be in some plane, depending where this thing releases you. With uniform acceleration downwards, it just becomes a 2-dimensional projectile problem within that plane. Okay, so anyhow, the magnitude of your acceleration, okay, if I've done this right, is this. This acceleration is going to kind of have a graph that looks like this one. Now, the point is, though, if you're riding this thing, you keep changing your direction, you'd think your acceleration would keep you moving, it would keep accelerating you forward, and you'd be pushed back in your seat, which would be true, except you're also curving, which means you feel a centrifugal force because you need a centripetal acceleration. Okay? Toward the center of whatever circle you happen to be on at this point. At every point, your motion, you could draw a circle that fits, a circle that's essentially tangent to the curve at each point. And the circles keep getting bigger because the curve in some way kind of straightens out, okay? So you want to get a handle on that. And I'm tempted to talk about it. But I'm just going to talk about the unit tangent vector. Okay? Now, this is for r equals t cosine t I plus t sine t j, and I'm writing it out very poorly, plus t squared k. Make sure I'm copying it down right. In other words, for this one and not this one. The direction of motion is the direction of your velocity. T is the unit tangent vector. I don't have room left to write out the next part of the statement, but the next part of the statement would just be that, well, your velocity is in the direction of your unit tangent vector. These velocities are always tangent to the curve, okay? If you want a unit tangent vector, you just divide the velocity by its magnitude. Divide the velocity by the speed, okay? So it makes sense. Since, again, the velocity is tangent to the curve, and you want a unit tangent vector because it's easy to work with, then T is just your velocity divided by its magnitude. It's not some mysterious formula that somebody handed down on a stone tablet. It's plain old common sense. Okay? As I always say, formulas are kind of like magic. Sometimes they work and sometimes they don't, depending how well you understand them. You might invoke the wrong formula for something. If you understand where the formulas come from, you're less likely to invoke the wrong formula. The formula is also useful too. If you have the formula and analyze why it's true, you don't totally understand it, but you learn to analyze why a formula is true, then you learn the same stuff, okay? And there are two approaches. You can start with a magic and then deconstruct it and understand where it came from. Or you can understand where it came from, and this is not a hard thing to understand, and ignore the stupid formula, okay? Because if you really understand this, the formula is kind of stupid to use a formula. Of course, you remember the formula and remember why it works. But it's the idea of taking a common sense idea like this, that the velocity vector is tangent to the curve, okay? And this is an obvious step, but this represents that obvious step, okay? So there's no magic involved in using this. There are formulas that you're going to end up with, maybe in this course, maybe in a later course. I don't know where the heck they came from, especially if you're an engineer. Okay, engineers use all kinds of formulas they don't totally understand. You just learn how to use them, because understanding every detail of every formula is kind of beyond typical human comprehension. And if you're not one of the people who can do that, there are just a handful, about one person in 10,000, maybe a million, I don't know, 100,000. Can understand everything all the way down to the details. So you just kind of leave those people alone. If people are leaving you alone, it's probably because you can do that. Okay. Maybe you're there. Maybe not. As I said, my grandson, a little more than halfway through his electrical engineering and tech. So yeah, some people you just can't compete with. And that's pretty much always true, except for just a handful of world-class minds. Anyhow, be prepared to get blown away. And if you're one of the people that blows everybody away, great, I love it. Okay, but don't count on being that person. And I so far you're doing everything great. So I can't judge what your potential is. By the end of the course, I'll have a pretty good idea. Okay. We're well on track to ace this course, and that's really good. Okay. Keep that up. Okay, so here's your unit tangent vector. And, we could write out the formula here. We just write out the formula for V, and then divide by square root of 2 plus t squared, right? So that equals, I have to write it kind of small, but I'm going to go ahead and do it. That's your numerator. All that over the square root of 2 plus t squared. Okay, well, I'm having too much fun to stop there, so I'm going to go on with this. Kind of lay the whole picture on you, because I find that I can usually do that with a pretty good group of students, okay? And since I usually have a pretty good group of students, I'm going to assume I've got one now, because that's all indications are I do. I'll just assert A dot t is a component of A in the direction of the velocity. If you're flying a plane or riding an amusement park ride with a complex motion, A dot t is a component of acceleration that feels like it's pushing you back in your seat. Of course, that's really because the seat has to push you forward to accomplish that acceleration. Okay? Now, why do I say that's a component of A in the direction of velocity? Well, t is in the direction of velocity because it's just a scalar multiple being 1 over square root 2 plus t squared times your velocity vector. Okay, t is in the direction of v. And I'm going to just draw a picture. Here's t. And let's say here's A. Now, magnitude of A will usually be bigger than the magnitude of t, but they're not commensurate. They have different units. But the vector A then projects back on t and this vector then is A dot t, the component of A in the direction of t. Now, if you don't totally understand that, you probably want to go back and review some stuff you did in the previous chapter, and it's straightforward. It's the projection of A on t. It's the projection on t of A. Since t is a unit vector, you don't have to worry about the magnitude of t. It's 1. And you got to divide by the magnitude of t twice. Okay? Once because the bigger t is, the bigger the dot product is going to be. So you got to unitize your vector here, which is already unitized. Okay. And so you have this projection, okay? And I say this is A dot t, well, that's the magnitude of this thing with sine. We got to multiply it by the t vector now. You know, if t wasn't a unit vector, that's where you'd also have to divide by the magnitude. You got a unit vector in the direction. So, anyhow, that we talked about all that, so review that. It's kind of critical that you understand that. Because now we know, if you know the formula for the motion and can do the derivative, in other words, your function has a derivative, okay, which pretty much all the functions you're going to look at do, then you can do these calculations, okay? And you can get this, and this is the component of acceleration in your direction of motion. This is how hard you're going to feel like you're pushed back in your seat. Assuming your seat is oriented so that the forward direction is your direction of motion. That's not always the case in amusement park rides or in jet planes. You can kind of, well, you can kind of slip in the stream and so forth. And I'm talking like I know a lot about it, and I don't. Yeah. Basic principles of aerodynamics, sure, but details. My grandson has 2 roommates in aerospace engineering. They could explain it. Maybe at junior level, okay? Hopefully by the time they graduate, because tech turns out great engineers. Okay. And even if they can't explain it, they can use a formulas to get the results. But I think they'll be able to do both. Okay. So anyhow, there we have it. To the unit tangent vector. Now, this picture, you also have another component. So I'm going to do this again. Okay, here's your unit tangent vector. And let's say, just draw it a little bigger so I can label it. Okay, well, we kind of extend this vector. So here's this. So we're going to call this component a parallel. The component of acceleration parallel to motion, which means component of acceleration in your direction of motion. That should be clear. So now here's a parallel, which we now know how to calculate, provided we can calculate A. Okay? Well, what do you think the other component is? Well, I don't want you to talk while this camera's on, because then we have legal problems. Ridiculous, but yeah, there's a point to it. Privacy is important. Okay, so there's another component. Okay? The other component's going to be perpendicular to A parallel, right? Well, you can picture that component very easily. This is A perpendicular. And so here's the vector A. Here's A parallel, here's A perpendicular. Now I'm going to turn the video off and we'll talk about this. I want you to write down, though, while I'm making the hike all the way over to the video camera, I want you to write down what you think in terms of the symbols in this picture alone. What A perpendicular is. A perpendicular equals what combination of vectors that you see in the picture.